Hi class, we are starting our next chapter, chapter 9. Chapter 9 is all about vectors. We're going to start with vectors in 2 dimensions and we're going to move into vectors in 3 dimensions later on in this chapter. Vectors are super important. They are the methods in which we create lots and lots of models to model lots of real physical situations. They're used a ton in physics. They're used everywhere in physics. In fact, all of classical mechanics is basically based around vectors. In mathematics, we have a course that's focused on vectors and the properties, and we call that linear algebra. It's a more advanced course. I have a whole video series on linear algebra and a course reader already written as well. Very interesting stuff. So, let's talk about vectors and what they are, how to do math with them, how to look at them graphically, and how to use them to solve problems, right? So again, they're a very important tool for describing the real world, okay? There are several characteristics and properties that come out of vectors, but the 2 most inherent properties that a vector has is that it has a length and it has a direction, okay? So whenever we talk about vectors, we always talk about what direction it's pointing in and the length of the vector. The length of a vector tells us basically, it's called the magnitude, right? So a long vector implies that there is more force, more direction, more whatever it is that the vector represents than a short vector does. Okay, so for instance, if we are talking about force is a good one. Okay, so like if I'm pushing against the wall, I can represent that with a vector. It points in the direction that I'm pushing, and if I'm pushing very hard, that should be represented by a long vector. If I'm barely pushing, that would be represented by a short vector in the same direction, right? So it doesn't matter where in space we place a vector, as long as 2 vectors have the same length in the same direction, they are the same thing. Okay, and so the length of this vector is the magnitude, right? If I'm pushing hard, a long vector has a large magnitude, right? If I'm pushing softly, a short vector has a small magnitude, okay? So you can think about that in terms of earthquakes, right? A large magnitude earthquake is a big earthquake. A small magnitude earthquake is a little earthquake, right? So again, if I have 2 vectors in space, it doesn't matter where I place them in space. As long as those 2 properties are the same, the length and the direction, then those 2 properties, or I'm sorry, those 2 vectors are identical. So let's look at this graphically. If I have a graph, let's say I have a vector A. Notice that this vector is not at the origin, but from one point to the other point, I move over 1 and up 2. So that helps me to point in a direction, right? And it helps me to kind of, on a graph, look at what its length is. Now, if I take this same vector and I place it somewhere else, let's say here, notice it has the same direction because it's over 1 and up 2, right? But it's in a different place in space. So it has the exact same length as this one, and it points in the same direction. So does C, and so does D. No matter where I place a vector that, from the starting point, I move over 1 and up 2, this will always be the same thing. It's literally, I can call this A and this A and this A. They're all the same thing. They're all the same vector. Okay. So there's a lot of notations that we use to signify vectors. Depending on what course you're taking, they'll change notations. For instance, physics they kind of have 2 different notations for vectors that they like to use a lot. If you're in engineering, they'll use a different notation. They tend to use the physics notation as well. Here I'm going to use the boldface notation. So one notation is a boldface letter, like we have here, okay, which I will use in this course. We have an A with an arrow on top, and we have an A dot. It's still a vector, but this is kind of a special vector. We also have an A dot dot, 2 dots on the top. Again, that's sort of a special notation, but it does represent a vector as well. Okay. So again, in this reader, we're going to stick with the boldface notation whenever we have a vector. So a vector has an initial point and a terminal point. Okay, so it has a starting and an end, and that is what tells us the direction, right? I start here and I end here, and I go from the start to the end, and that's where my arrow points in. So all of these vectors point in the same direction. So again, they have to have the same direction, and they have to have the same magnitude, the same length. Okay, so the initial point is the tail, and the terminal point is the tip, the arrow tip of the vector, right? So initial point and terminal point. So start and finish. I can change the scale of a vector by multiplying it times what's called a scalar. That should make sense. If I'm scaling the vector, I'm changing its scale, how long it is, right? I'm multiplying it by what's called a scalar. A scalar is really just a real valued number. Okay, so pi, 2, 1/2, square root of 3. I think I've referred to these as scalars before when we've talked about things. I say, for instance, like a function, we're going to multiply this by a scalar amount. We're going to, take this function, multiply it by 2. All the values in this function are now doubled. Same thing with a vector. I can scale the value by multiplying it by a real value. We call that a scalar. So it's going to make it longer or shorter, but it will still point in the same direction. Okay, so again, we call this a scalar value. It's any real number. So if this is my original vector A, I can scale this by multiplying it by 1/2. Now it points in the same direction, but it's half of the length of the original. Okay, I can multiply this by a value of 2, and now it's twice the length of the original, but it points in the same direction, right? So I've just scaled the vector to be longer or shorter. I can also multiply it by a negative scalar, which makes it point in the opposite direction. So if this is A, negative A means it's the exact same length, but now it's just pointing in the opposite direction, right? Very much so like if you think about when we're doing polar coordinates and we took our radius and we use a negative radius with a different angle to represent the same point in polar coordinates, right? Very, very similar. So I can multiply it by negative scalars, which will, take its value, double it, and then point it in the negative direction. Okay. So when we add two vectors, there's a couple of methods we have for adding. Okay. And I'm talking about this in a geometric sense, right? We haven't really talked about how to do this algebraically yet. We're really just looking at the geometry of these things. This is what a vector looks like. This is what it looks like when I scale its value. This is what it looks like when I multiply it by a negative scalar and change its directions, right? So when I start to add them, there's two methods of geometrically adding two vectors. The first one is called the parallelogram method. For the parallelogram method, what happens is we take our two vectors that we're trying to add together and we place them initial point to initial point, right? So we're basically connecting the initial points of the vectors. What happens is this creates the basis, the outline of a parallelogram. It gives me two sides of a parallelogram. So then what I do is I trace out the remainder of the parallelogram, and then I draw the diagonal that spans from those two initial points of my vectors where they connected. Okay, so as steps, again, I'm going to place my vectors tail to tail, and I'm going to draw out my parallelogram. Okay, I'm going to connect the initial points of my two vectors, and I'm going to draw the diagonal that is created from that point. So let's look at this in terms of an example. So here's a vector A. It points in this direction and has this length. I'm going to add it to a vector B, which is longer and points in this direction. So what I'm going to do is I'm going to put these tail to tail. Okay, tail to tail. So here's B, here's A. These are literally the exact same vectors as well. I did not change their size or anything, but you can see that this one is down a little bit from this one, but they are the exact same vectors. Okay, this gives me the base, right? Two sides of a parallelogram. So I'll extend a parallelogram by drawing out the remainder of it, right? So remember, a parallelogram is a rectangle, square, anything, and it can be off kilt because it's basically just a four-sided figure. So here's the parallelogram that's formed. Now from the point where the two vectors are connected, this initial point, I'm going to draw the diagonal that goes with this point here. Okay. So this resulting vector here is my vector A plus B. So I took A, I took B, and I drew out my parallelogram, and then I connect the diagonal that's formed from that, and that is my addition of vectors. So if I add two vectors together, I get a new vector. Okay. The second way of adding two vectors together is the tip to tail method, and it's just as you think, you put them tip to tail. So here, the parallelogram method, you can also think of tail to tail, right? Because you're connecting the tail of one to the tail of the other, and then you're drawing a parallelogram. But it's easier just to remember them as parallelogram and tip to tail. So tip to tail is you take one vector and you place your other vector, you place its initial point at the terminal point of the first vector. Okay. From there, you just connect the two vectors. You basically make a triangle out of them, and that new resulting line is the addition of vectors. Okay. So here we have A plus B. So I'm going to place the end of B, the initial part of B at the end of A, or vice versa. I can take B and I can put the initial point of A at the end of B. It doesn't really matter which one I do, but here we're going A and then B, so I'll go in that order. So I got A first, and then I'll go B, and then to finish out the triangle, that's this line here. Okay. So if you notice, this is a straight line up and down, and this is a straight line up and down. I use the exact same vectors for both of these, and so it's apparent that we have the exact same sum. Okay, it is this vertical line here is the sum of our two vectors. So you can use either method whenever you want. Sometimes one method is easier to see than the other. Sometimes the other one is easier to use. Most of the time, however, though, we just add vectors component-wise, which is the algebraic method of adding vectors. But a lot of times when we're in drawing diagrams, we have to recognize that we have one vector and another vector, and in order to add them together, we're creating a parallelogram, or we are creating this triangle. Okay. Another thing I want to point out is, if you notice, this right here is that triangle that we created here as well. And if we want to subtract two vectors, we do the same thing as we did before. However, it's easier to think about it as an addition of a negative scalar of a vector. So we add the two vectors, but one of the vectors we just point in the opposite direction, and we can use either of the two methods that we had before. Okay. So if I have A minus B, geometrically it's a lot easier to think of it as A plus negative B. So I would take my A, I would add my B to it, I would draw it, either as a parallelogram or as the tip to tail method, and then I would reverse the direction of B and then draw whatever it is I need to draw to find that A minus B value. Okay, and that's the easiest way to subtract two vectors geometrically. So now that brings us to the discussion of the component form of vectors. The component form of vectors is talking about the pieces that make up the actual vector. So when we came over here to this initial discussion of drawing a vector on a graph, I pointed out that this value of A is over 1 and up 2, no matter where it is in space. Over 1, up 2, over 1, up 2, over 1, and up 2. So this vector has an x value of 1, because from one point to the other, the distance in x is 1, and a y value of 2, because the distance from one y value to the other y value is 2. So that's the components that make up this vector. If it was 2, 2, for example, I would go over 2 and up 2, and then I would draw my vector from its initial point to its terminal point. So the way that we use the component forms of vectors is by discussing how long is the x portion of it, right, the horizontal portion, and how tall or small is the vertical portion of it. And so that's how we discuss our component forms. Okay. So if I have an initial point of P, which I'll call x naught, y naught, and a terminal point, which I'll call Q, which will be x1 and y1, then the difference in the x values, my delta x, is the x component, and the difference in the y values, delta y, is the y component. Okay. So if I want to talk about A in terms of its initial point and terminal point, I subtract the x values and I subtract the y values. And that will give me the x distance and the y distance of my vector A. Okay. So, again, there's numerous ways to represent a vector, just like we had different notations for the name of vector, right? Bold-faced, A with an arrow over it, A with a dot over it, things of that nature. I can represent the component forms in multiple ways as well. In fact, there, off the top of my head, I think we got about 3 standard ways. I'll discuss 2 right now, and the other one we'll discuss as we progress through our discussion of vectors, right? So, let's see. We have different types of brackets. We can do a horizontal representation, a vertical representation, and we can do what is called a standard vector, standard unit vector representation. Okay, so A I can represent as A1, A2. So this is pretty much the standard that you'll see everywhere. So we have these brackets on either end. Sometimes they'll be written in parentheses. A lot of times people try to avoid this, however, because it's really easy to confuse this as a point in space, although that's pretty much kind of what a vector is for the most part. We can also represent it vertically as a vector in this form. So when you take a class like linear algebra, this is generally how we represent vectors in a linear algebra course. Okay. So let's talk about the magnitude of a vector. So if you haven't made this connection yet between a vector on a graph and something else that we've done in this class, here we go. Okay. A vector is a line, has an x component and a y component. That creates a triangle for us. Okay. Which means that our entire discussion of trig that we've had already in this class applies to vectors. Okay. So a lot of what's going on with vectors has a lot to do with trigonometry. Okay. So let's come back here to where previously. So if I want to find the length of a vector, the magnitude of a vector, I'm basically using the Pythagorean theorem, right? So again, a vector is a line that connects 2 points in space, and the length of that line is the length of our vector. So if my vector is given by an x value of a1 and a y value of a2, then the length of A, or the magnitude of A, also called the norm of A, is the square root of the individual terms being squared and added together, right? It's the Pythagorean identity. So again, the length of the vector is called the magnitude or the norm of the vector. Okay, so we won't use norm too much. It does get peppered in, but when we start getting into calculus, we do refer to the length or the magnitude of a vector as its norm. Okay. If we have the component vector form of 2 vectors, then we can add those 2 vectors algebraically component-wise, meaning the 2 x values add together and the 2 y values will add together. Okay. So if A is A1, A2, and B is given by B1, B2, then if I want to add those 2 together, I add their 2 first terms together and I add their 2 second terms together, right? So component-wise means their respective components get combined together. So that is the definition of the addition of vectors algebraically. If I want to multiply a vector by a scalar, right? Remember, we can scale its value. All I'm doing is multiplying each component by that scalar value. Okay. So if I want to scale it by a value of lambda, so make it larger or smaller by a value of lambda, then I would multiply each component by lambda. Okay. So lambda is just a real number. This does affect my length because think about what happens in here. If I have lambda, this is lambda a1 squared, a1. When I do this, I square lambda as well, and I square lambda as well here. That's a common value, common factor of lambda squared. So then that gets square rooted and it gets pulled out, and I end up multiplying the length by a value of lambda. So I'm sure that will be left as a discussion or a homework problem later on, or an exam problem at some point. So it's very important to be able to recognize that. So let's look at an example. So let's say we have a vector A that's given by an initial point of 1, -2 and a terminal point of 3, 1. Okay, and then we have a vector B with an initial point of 2, -3 and a terminal point of 3, 0. We want to find a new vector C that is made up of 2 times A minus 3 times B. So in order to do this, we first need to find A and B. So let's find them in terms of their components. So to find A, we find the difference between the y values, right? So we have the starting point, the ending point. So it's the end minus the start. So 3 minus 1 gives me a 3 minus 1. Then we have 1 minus a -2. So then the components of this vector are 2, 3. And if I want to find 2a, I then take this vector and I multiply each component by the scalar 2. So that turns into 4, 6. To find b, I do the same thing. I got 3 minus 2 and 0 minus a -3, which gets me out 1, 3. I multiply this times the scalar -3, and so each term multiplies by a value of -3. So now I can add 2a and -3b together because I need to add these. I could have just multiplied these times 3 and then subtracted them. That's fine. You don't always have to use the negative scalar. You can just use a scalar and then subtract your two values. Okay. But in order to have 2a minus 3b, I will have my 4 plus -3 or 1. Okay. Let's put these components. 2a plus -3b. So 4, 6 plus a -3, -9. So we have our 1, and then we have our -3 here. So my vector C is 1, -3. Let's say that I want to find the magnitude of this vector. What is its length? Well, I take its individual components, which I just found. I square them. I add them together, and then I take the square root. So this will give me 1 plus 9, or square root of 10. Okay. If we have a vector that only has zeros, we call that the zero vector. Okay. So the zero vector is a vector made up of all zeros. Okay. So notice that in the xy rectangular coordinate system, every vector has only 2 real elements. So the collection of all of these vectors is called R2. Okay. So again, when we're in xy, all vectors in xy make up what's called R2. Okay. So properties of vectors in R2. So let a and b be scalar values. So a and b are real numbers. Let u, v, and w be vectors in R2. Okay. U, v, w, in R2. Then, if I add two vectors, it doesn't matter the order that I add them. So we call this the commutative property of vector addition. So I can add u plus v, and that'll be the same as v plus u. It doesn't matter which order I add the vectors together in. Okay. If I add two vectors, and then I scale that sum by value a, it's the same thing as if I were to scale one of those vectors times by a, and the other vector by a, and then add them together. So this is the distributive property of scalar multiplication, right? Here, a plus b is a scalar because those are both scalars. So if I add two scalars together and multiply times u, it's the same as if I were to scale that vector u by one value and then scale it by the other and then add that result together. Okay, so this is the distributive property of vectors. I can distribute across my scalar. If I have three vectors that I'm adding together, I can add u and v together first and then w, or I can add v and w together first and then u, and they'll be equal. This is the associative property of vector addition. Here I can multiply b times u times the scalar, or I can multiply a and b first as a new scalar and then scale my vector, and it's the same. So it's the associative property of scalar multiplication because it doesn't matter which scalar I apply first. Here if I have a vector u and I add it to what's called the additive identity, which in general is just the negative of all these vectors, I will get out the 0 vector, right? So it's the additive inverse property. Here, if I add u plus the 0 vector, it's the same as the 0 vector plus u. So this is the additive identity property. And last is that if I multiply u by the scalar 1, I will get out u itself, which is the multiplicative identity property. Okay, so when you take a linear algebra course, this is the basis of what we study in linear algebra. This forms the foundation for everything, and it's a big deal. Okay, so we can use this to show that there are lots of things that we consider vectors, not just the vectors we've been studying, right? So things like matrices can be considered as vectors, functions can be considered as vectors. There's lots of things that we can consider as vectors. Okay. So vectors in terms of I and j. So we call I and j the standard unit vectors. Okay, there's actually a third one called k, which we'll talk about later on in this chapter. It comes into play when we start talking about things in 3 dimensions. Okay, any vector of length 1 is what we call a unit vector, right? So as if the magnitude of our vector is 1, then that vector is a unit vector. The standard unit vectors are the vectors that lie on the axes, right? So I is a length of 1 and it lies on the x-axis. J has a length of 1 and it lies on the y-axis, right? So I is just 1, 0. It has a length of 1 and it is 1 unit along the x-axis. J is 1 unit along the y-axis, right? So any vector can be written in terms of these standard unit vectors, right? Any vector in R2 can be written in terms of I and j. So for instance, if I have a vector A that's written as A1, A2, I can rewrite it as A1 times 1, 0 plus A2 times 0, 1. And that should make sense because what happens if I add this? I get A1 plus 0. So just A1 in the first component portion. A1 times 0 is 0 plus A2 will just give me A2. So I can separate this in terms of A1 times its unit vector in its direction and A2 times its unit vector in its direction, right? So this vector A is A1 units in the x direction and A2 units in the j direction. So I can separate this into i's and j's. This is a standard notation that we use, especially in physics. Physics, we don't tend to use this notation too much. We tend to use this I-J notation. This is more of a linear algebra thing. Math, this is more of a physics representation of the same system. Okay. So again, since vectors are only defined by their length and direction, not their actual position in space, we like to place vectors so that their initial point is at the origin. It just makes things easier to work with. That and then their terminal point will always just lie at their components, right? So if this is 2 and 3, if I place the initial point at the origin, I could just plot the point 2, 3 in space, connect it with a line, and there's my vector. Okay, so again, position doesn't matter, orientation doesn't matter, just direction and length. Okay, and that allows me to utilize a lot of our trigonometry really easily. So again, if this is A1 and this is A2, instead of placing it way out here, I just set the initial point at the origin, and it makes it really, really easy for me to start to analyze my graph and start to create this triangle and analyze all the things that I can from it, right? So this will be my length of A. This will be cosine of theta times the length of what is now a radius, right? And this will be the magnitude of A sine theta. So I can represent my vectors geometrically in terms of brackets, in terms of I and j, and I can also represent them in terms of not just x and y, but in terms of their magnitude and their angle. Okay. So horizontal and vertical components of a vector. So if A is A1, A2, I can rewrite it as A1 times I, its horizontal component, and A2J, which is a vertical component. But typically when we refer to horizontal and vertical components, we don't refer to the standard unit vectors, we refer to the cosines, okay? A1 can be written as magnitude of A, cosine of the angle it forms, times its horizontal unit vector. Its y value, in terms of its magnitude and angle, times its y unit vector. So this last form right here is the horizontal and vertical component of the vector, right? And if I want to, I can put it back into parentheses and get rid of the ij notation, and I can write it this way. So these are the four forms that you will see vectors written in all the time. They're interchangeable. Sometimes they'll be written in the first one, sometimes they'll be written in the last, sometimes they'll be written as ij's, sometimes they'll be written with ij's and the magnitudes and angles. So we have to recognize that these are x's and y's. Okay. So the last form again is comprised of the horizontal and vertical components of A. So this brings us now to force and velocity. So now we have all of the discussion of the components kind of finished. So now we can talk about using these things. So we know how to add them, multiply them. We understand the scalar idea. We've related it to our triangles. So now we can talk about representing things in terms of vectors. And the main uses of vectors, as far as like classical mechanics goes and representing systems and situations, is by talking about force and talking about velocity. So an example of this is, or an application of this is video games. If you ever play video games, all of the code for your video games, for most video games, are written in terms of vectors, force vectors and velocity vectors, right? If you're playing a basketball game, when you throw the ball, it has a direction, it has a velocity or a force that is being applied as well for it to reach the basket, go over the basket, not reach the basket, reach another player, what have you, right? So pretty much every video game is basically comprised of a set of laws of vectors that are pre-written into the code. And then, you just put the animations on top of it, okay? So again, the two main uses of vectors are to represent velocity and force. So when we draw diagrams and things of that nature, we're generally talking about force and velocity. A velocity vector is used to model an object's velocity, right? It makes sense. The magnitude of a velocity vector tells us the object's speed. So for instance, if you're talking about a car on a highway, you will have a vector that tells you the direction it's going. The length of that vector will tell you how fast it's moving, right? If a car is moving slow, we'll draw a small vector. If a car is moving fast, we draw a large vector, right? So again, speed does not have a direction, so speed itself is not a velocity, but velocity does have a direction, and it does have a length, right? A lot of velocity, a little bit of velocity, and it moves in a certain direction. If I'm going a speed, right? If I'm going 12 miles per hour, I'm not telling you what direction I'm going. Am I going 12 miles per hour forward, or am I going 12 miles per hour in reverse? You don't know, right? But a velocity vector tells you you're moving forward, backward, side, up, down, what have you, right? So just a quick clarification there. The magnitude of a force vector tells you the amount of force being used. So again, I use my example of pushing an object or pushing against the wall, right? If I'm pushing with a lot of strength, a lot of force, I have a large magnitude, right? If I'm barely pushing something, that is a small magnitude, small amount of force. So again, the longer the velocity vector is, the greater its speed. The longer force vector is, the stronger the force that's being applied. So let's go ahead and do an example. Okay, so let's say that we have a 150-pound sign that is hanging from a beam by a wire, as shown below, which we'll see in a second. We want to find the tensions T1 and T2 in the wires. So we have a beam. There is a wire here and a wire here that is holding up a sign that weighs 150 pounds. The angle created with the beam by the weight of the sign is 20 degrees here, 45 degrees here. the tensions in the wire are what is holding up this weight, right? So this weight is being pulled down due to gravity. So it's pulling on these wires. So there's actually an opposite equal force by each of the wires pulling in the direction of its connection. Okay, so that's one of the Newton's laws of physics, right? For every action, there's an opposite and equal reaction. So T1 plus T2, these two forces have to equal the opposite force of this 150-pound weight being pulled down by gravity, right? So opposite and equal, right? So these two have to counteract this force. That's why it's hanging and not continually falling to the ground. If it was heavier and not equal to this, these wires would snap, right? These wires are not having more force than the weight of this object, because if that was true, it would be moving in an upward direction, right? It's an equilibrium. It's not moving at all. So the forces are counteracting each other. Okay. So if we want to answer this question, we should put these vectors on an axis, right? That'll help us to solve some things, because as it is free floating in space, it's a little bit weird. Okay, so there's a few laws from geometry that we should probably discuss, because again, I don't know how familiar you are with geometry at this point. It's called the law of transverse lines. Okay, so if I have two parallel lines and I take a line that intersects those two parallel lines, then these two angles, these set of angles, are all the same. This angle is the same as this angle. This angle and this angle is equal. This angle and this angle is equal, right? So the angles opposite of each other are equal. Same thing here. These angles are equal, and they're equal to these two angles here as well that are not being shown. So if I take this drawing that I have here, make it a little bit larger, pull it on the side, you can see that it actually lines up a little bit. This beam here lines up with this line, and we will draw an axis here that lines up with this line. Okay, so there's one line, and there's the other parallel line. This line here is this same intersecting line, okay, which means that this angle, and if we continue this down here, would be the same as this angle. Okay, so this angle is equal to this one, right? So again, if this is my drawing, I have this line and this line with this one. So these two angles are the same, right? We have one side and this side, right? That's this one and this one. Parallel line, the transverse line, inside angle, across the line, inside angle, across the line, inside angle. Same thing here, but it's the opposite. So I'll draw a secondary line here to signify that this is a different angle. That is equal to this secondary angle here. Same exact rule. Okay, inside and inside, two parallel lines. So that's how we can form this relationship, right? So I know that this angle with this horizontal is 45 degrees, and this angle with this horizontal is 20 degrees. So if I want to, I can pull this out into its own complete axis and talk about these two vectors, T1 and T2. Now, notice again, as I said before, that this is being pulled down due to gravity, right? And so the direction is straight down, and the magnitude is 150, right? Weight is a magnitude. Weight is not a vector, right? If it's moving with gravity, right, that is a force, so that's a velocity vector. However, it's stagnant, and the magnitude of that, the force of it, that weight, is 150 pounds. So let's put this on a graph. I have T2, I have T1. I know this is 45. I know that this is 20. I have another angle here that points in the negative direction with a magnitude of 150. So let's write these in terms of components. So first I'll use T1, right? If I want in component terms, I have no idea what the length of this is. That's literally what they're asking me to do. Find the tensions, which is the magnitude of T1 and the magnitude of T2. Okay. So my T1 vector is its magnitude times cosine of 180 minus 20, right? This is 180, subtract 20, that gives me my 160. Here, again, we're still on the y, so my sine value, my x value is the same angle, right? That's the angle that's created. Right, so I want to use 160 because, again, this is 160 degrees. This is the 20 degree vector, it points in this direction. So my cosine will be negative, so I need to make sure I'm using the right angle when I do this. Okay. So I have T1 cosine 160, or I can call that negative magnitude T1 times cosine 20. And then my T1 sine of 160 is the same as 120, right? It doesn't matter for this one. So T1 I can represent with this vector in its horizontal and vertical components. T2 I do the same thing. It's just a standard 45. I don't have to do any adjustments with angles. So magnitude of T2 cosine 45, magnitude of T2 sine of 45. Okay. So the wires are holding up our sine. So I know just a second ago I said I need these magnitudes. I don't need these. I do need the magnitudes, but the tensions themselves are not magnitudes. I want to just clarify this. I'm trying to find the full vector representation. In order to find the vector representation, I need the magnitudes, is what I meant to say there. Okay. So the wires are holding up the sine. The sine wants to fall downward due to gravity. The wires have to work against gravity to keep it in equilibrium. So adding T1 and T2 together plus T3 will equal 0, right? Or another way to think about that, T1 and T2 are equal to and opposite in sign of T3, right? That's that Newton's law that I was discussing. So I know the magnitude of T3 is 150. That's the weight that it's being held onto. And I know its direction is 0, y3. I'm going to call it y3 because it's the third vector, and T3 is the third vector, that's why, right? So I know there's no x and y movement if I'm considering this as the origin. Okay, this is the origin where all three are kind of connected, but it is moving in the negative direction of y. So no x direction, but only y, and it's actually in the negative direction. So my y3 value should be negative here. Okay, so I know the magnitude is 150. I know it looks like this. How do I know that it's negative 150? Well, think about this. The magnitude is 0 squared plus y3 squared square rooted. So that's 150, and it has to be in the negative direction. So my y3 is negative. Okay, so that's nice because now I have one part of the equation. So I can substitute in my T1, my T2. I know an actual value of T3, so I have an actual equation. So my T1 horizontal component plus my T2 horizontal component has to be 0, right? Because again, it's equal to but opposite direction of T3. T3 has 0 here, so x value plus this x value has to equal this x value, right? So I take the two horizontal components, add them together, and I know what it has to be. I can do the same thing for the y components. The y component of T1 plus the y component of T2 has to equal the y component of T3, right? So I get sine of 20 plus sine of 45 equals negative 150. And the reason why it's 150 and not negative 150 is because it has to be opposite in sign. So this is a negative 150, right? It's opposite and it's equal to and opposite in value. The signs here are in the positive direction. The T3 is in the negative direction, so it has to be opposite in value. So very important that when you're doing a problem like this, you remember that you have to change the value. So since this is negative, this one has to be positive. It changes sign. Okay. This gives me two equations now. Okay. These are actual values with two unknowns. I don't know T1. I don't know T2. Right? Those are my variables, my unknown values. And I have two equations. So I can solve for the magnitude of T1 and I can solve for the magnitude of T2. And once I do that, I then can figure out what T1 and what T2 is. So remember, cosine of 20 and cosine of 45 are actual values. Sine of 45, sine of 20 are actual values. This is some number times this unknown, right? Some number times this unknown. So I just have to plug those values in. So with my first equation, using these values, I can set them equal to each other because one was negative and the other positive. So I'll just add one over. Okay. So T2 cosine 45 is the same as T1 cosine 20. So again, I'm going to save the decimal approximations because cosine 20 is going to be a decimal value unless I use some crazy trig formulas, addition, subtraction formulas that I don't really want to bother with. I'll just move everything around until I'm ready, and then I'll get my decimal approximation, right? So I have, if I plug this in, remember cosine of 45 is root 2 over 2. If I want to think about it as a scalar, I'm going to multiply by the reciprocal, right? It's going to flip over. So that's why you have a 2 on top and a root 2 on bottom. I can't solve explicitly for T2 just yet because I don't know what T1 is, but I can take this and plug it into my other equation somewhere, right? So I know what T2 is. So if I plug in T2 for that value I just found for T2, then I'll have an equation that is only in terms of the magnitude of T1, which is what I want, right? So here we go. I can simplify a little bit further if I rationalize the denominator. So I'll plug that into our second equation, this one. Okay, so where I see T2, I will replace it with magnitude T1 root 2 cosine 20. All right. I will pull out that common factor of T1. I'll apply this root 2. You know, I'm simplifying things as much as I can as I go. Here it's nice because this root 2 times root 2 is 2. Over 2 is just 1. So it turns into T1 sine 20, T1 cosine 20. Pull out that common term of T1, and then divide both sides by this sine 20 cosine 20. Okay. There's nothing left for me to do math-wise except for find my decimal approximation, right? So that's approximately 117.0309013. Okay, I don't need all these values, but for right now, I'm going to keep them. Now that I know what T1 is, I can come back and find T2. Technically, when I find T2, I'm not going to use this decimal approximation. I can, it's probably okay. But what I'm going to do is I'm going to plug in for T1 this exact value and then calculate this thing exactly. So I'm not playing around with decimals and I'm getting everything that I need exactly, right? So I'm going to plug in T1 here for my T2, then plug it into my calculator, and I'll get about 155.5254133, right? So those are the magnitudes. So now that I have the magnitudes, I can come back and I can plug them in for my T1. It's negative 11703.0901 cosine 20 and sine 20, which I can then evaluate and get its components, and I can do the same thing for T2 and get its components, right? And so that is how we solve problems with vector equations.